with the addition of spin, the Schrödinger equation we've been using is obviously not enough. And we're certainly not going to get the correct results as soon as we have to deal with magnetic fields. Additionally, if we're considering the effects of magnetic fields, we should add in the ordinary interaction of an electron with a magnetic field, which we've so far not included in our Schrödinger equation. We left out that interaction between magnetic fields and charged particles so far, in part because that interaction cannot, in general, be written using a simple scalar potential. The effect of a magnetic field on a charged particle depends on the velocity of the particle in ordinary classical electromagnetism. So the particle can have energies that are neither just due to position, as in a classical potential, nor just due to kinetic energy. We can deal with both the spin effects and the magnetic field effects using an extension to the Schrödinger equation called the Pauli equation. We won't go through all the derivation of that, in part because it would involve yet more classical electromagnetism involving that vector potential. We can, however, at least sketch how it is put together.
Classically, because angular momentum is a vector, then electron spin would also be a vector. And we could call that sigma. Then we would expect a magnetic moment of this form here in a vector generalization of the scalar version of that. In this classical analogy, and it's only an analogy here, with this magnetic moment, the energy associated with that magnetic moment in a magnetic field, written out here in terms of its components in the x, y, and z directions, would simply be this energy, mu dot b, and that would be this term here. In the quantum mechanical case, as usual, we postulate an operator instead of the classical quantity. So instead of Es, this classical energy, we have with our Pauli spin operator, sigma, an expression like this. G mu b sigma dot b. We have a factor of 2 here. I'll explain why that is there. It's not actually a change in the physics. And so writing this out in terms of the Pauli spin matrices, this would be our expression for our presumed quantum mechanical Hamiltonian here. As I said, in this expression here, we have a factor of 2 compared to the classical one. But this factor of 2, the factor of a half here multiplying this expression, is actually only because we like to work with Pauli matrices with eigenvalues of unit magnitude. It's just a choice that we made. We did not have to make that choice. It actually introduced a factor of 2, and we're taking that out again here. So that's rather than the half integer magnitude that's really associated with the spin itself. So the sigma numbers were plus or minus a half for the magnetic quantum number, as it were, of the spin. But the sigma operator is defined with the factor of 2 already in it on the bottom line. It does not express any other difference in the physics. So the Pauli equation includes this energy term that we have at least rationalized here. The Pauli equation also treats the electromagnetic effects on the electron as a charged particle, semi-classically, that is, with classical electric and magnetic fields. So by an extension from classical electromagnetism, it uses P minus E times the magnetic vector potential instead of just the momentum operator P. This, in the classical version with just momentum minus E times the magnetic vector potential, is a standard substitution that allows us properly to include the effects of magnetic fields in particular on electron motion. And we won't justify that piece of classical electromagnetism here, though it is a standard result. Anyway, quantum mechanically now, instead of the momentum operator in our Schrödinger-like equation, or our Pauli equation, we're actually going to use this instead, which, as I said, can be justified by analogy with the classical electromagnetism of charged particles. And we're going to use that to construct the rest of the energy terms in our equation. Hence, instead of the Schrödinger equation, we have the Pauli equation. Instead of having essentially p squared over 2m naught, we've got p minus Ea all squared over 2m naught. We still have the potential here, which could be an electrostatic potential. And additionally, we have this term, which is the effect of the magnetic field explicitly on the spin of the electron. This term handles all of the effects of the magnetic field on the ordinary motion of the charged electron particle. And this one handles the effect of the magnetic field on the spin. So this is like our Schrödinger equation. We've substituted in p minus Ea instead of the momentum operator, and we've added this term here in to handle the spin. Now, note that this psi is actually a spinor. So this Pauli equation is therefore not one differential equation. It's in general two coupled ones. And they're coupled actually through this term in the Hamiltonian. More rigorously, since we think of sigma hat as a 2 by 2 matrix, we should actually introduce the corresponding 2 by 2 identity matrix IS, this would be a 2 by 2 identity matrix, and we should write out the equation like this. So we should have an IS in here to make this term into a 2 by 2 matrix. We should have an IS in here to make this term into a 2 by 2 matrix. This one already is a 2 by 2 matrix. Then we would properly be adding up 2 by 2 matrices to get something in here that was a 2 by 2 matrix. So then, everything in the curly brackets has the 2 by 2 matrix character needed for the spinor. Though in practice, this identity matrix is just assumed. We usually do not write that one explicitly. The Pauli equation, which we've just written down, is the starting point now for investigating the effects of magnetic fields on electrons. It can be used, for example, to derive the Zeeman effect that we introduced somewhat informally earlier on in this discussion. And that could be derived including the effects of spin as well as the effects of magnetic field on the orbital motion of the electron.